So I'm Zain Rizvi. I'm part of the AI Platform Notebooks team, and I will be talking to you about how you can accelerate your machine learning workflows with AI Platform Notebooks. So here's just a little bit about myself. I've been at Google for about 2.5 years. Before that, I spent 8 years at Microsoft working on the Azure and Windows teams. And on Windows, we had a really fanatical obsession with how do you make your binaries build reproducibly, which is something that's now transferring over into the notebooks world as well. And up there, you can see my info on Twitter, blogs, and a podcast that I co-host. And so now let's begin. So start off with describing the state of the union. What's going on? Why is this talk even necessary? Why do we need to worry about speeding up our flows? And then we'll go into some techniques to help you analyze your data much faster. We'll follow up with how you can implement all of those techniques really easily on AI Platform Notebooks. Then we'll have a quick recap over everything at the end. And now, let's begin. State of the union. Data scientists and machine learning experts have come up with a whole bunch of really cool use cases from all the data that we've been collecting over the past few decades. People have been able to use this to figure out how to detect cancer really easily and automatically. Factory workers and manufacturers have been able to figure out how do you detect which machines are about to go into failure, so you can run whatever they're going to fail, so you can run preventative maintenance on them really quickly before any catastrophic failure occurs. And even farmers have been getting the ML action, using things like big data to figure out when is the best time to feed their shrimps, so the shrimps are happy, healthy, and delicious. Now, let's look at the basic workflow of data science. You start off by taking your data. You take a sample out of that data, so you have something that's much more manageable. You pre-process the data, clean it up, make it more amenable to machine learning techniques. You experiment with a model, and you train it. You try to figure out, hey, how good is this model? First time you do it, it's probably not going to be all that great. So you iterate over through this a few times until you arrive at a model that you think has a good potential. Once you do there, you run that model and train it on your full data set. Now, the full data sets are often really, really big. The training can take anywhere from hours to days to even weeks. And this process, once it's done, first time you do it, chances are you're not going to have as good of a result as you hoped for, so you go back to square one. And you go through this loop over and over again until you arrive at a good result, which often leads to something like this happening, where you end up having a lot of time spent just waiting for your analysis to run. So what do we get by training faster? You get to maximize your productivity. You don't spend time waiting around. You actually get to those insights much faster, and you can experiment more. You can do more. But all these faster results mean you can constantly iterate much more. You can try more experiments. You can explore deeper into the data set, getting at insights that you just would not have had the time or opportunity to get to otherwise. So how do you do this? Classic technique, get a stronger computer. This was something that was really popular for decades, especially in the heyday of Moore's Law. It became a little bit harder to do once you started running into the limits of what a single processor could do. At that point, you had to start distributing the work amongst multiple cores on the same computer, which added some complexity. You had to figure out how you implement your algorithms to take advantage of the parallelism. Fortunately now, a lot of the libraries and packages take care of that complexity for you. So this remains the easiest option for speeding up your workflow. But oftentimes, a single machine is not going to be strong enough to meet your needs, no matter how many cores and RAMs you can fit into that machine. There's a limit to how much a single machine can take. So what do you do in that situation? Use a whole bunch of machines. Get a cluster, split up the work and you can get way more CPU and memory at your disposal when you do things this way. Of course, it comes with its own limitations and its own complexities that are added on, but this really lets you get a whole lot more processing power that you can set on your data. And then finally, use GPUs. That's what you guys are all here for, right? A single GPU offers hundreds or even thousands of cores that you can use to really, really supercharge your data analysis. And if you notice, as you're going from left to right, really what's happening here is you're getting more cores. You're getting more cores at your disposal, and more cores really means you can parallelize your data into greater and greater chunks. So really what this comes down to at the core is how much can you parallelize your data? How well is your algorithm situated to parallelizing all of it? And the more you can parallelize what you have, the faster you'll be able to crunch numbers. And now, notice I've given you 3 different techniques so far. Each of these techniques comes with its own benefits and its own drawbacks. And so these are all really different tools that you have at your disposal. And as engineers, it's up to you to figure out what's the right tool for the job. Different workflows will work better with different tool sets. Now, how do you actually do this? AI Platform Notebooks makes it really easy. And what is AI Platform Notebooks? This is a managed Jupyter Lab environment that brings you support for all the really commonly used data science and machine learning libraries. We've got built-in support for things like TensorFlow, Rapids, PyTorch, and a whole lot more. So you can focus on actually running your algorithms and figuring out what models you want to use and not worry about how do I get my stuff to install. And it comes with a lot of goodness out of the box. Things like Git integration and supporting with GitHub, so you can have your code living on GitHub. And we come with a whole bunch of really cool enterprise features baked in. Things like customizing your test environment by bringing in your own container. If you've ever tried to run a notebook that a coworker of yours created, you may have run into this issue where you try to run the notebook and it won't run. Why? Because they've got a whole bunch of packages that they installed that are not in your box, and you have to figure out what those packages are, install them. Maybe you have to figure out the right version of the package because they use a different version, and you have to track it down to exactly what was being used. This adds a whole lot of friction to your workflow, which you don't really want to have to worry about. If you create a custom container for your entire team, that means your entire team will be using the exact same set of dependencies. And if a notebook builds on one person's notebook, like on one person's machine, you can port it over to your own and run it just fine without any issues. And if somebody has a new dependency, you just add it to that base container, and everyone will have it automatically. We make it really easy to share notebooks with the rest of your team with AI Hub integration. This is really useful for sharing notebooks with people who might not have access to your source control, but you still want to give them access to your notebooks. There's advanced networking options for enhanced security. Make sure that you can really lock down your notebooks if you have extra high security needs. It's HIPAA compliant, and it's integrated with identity access management so that the only people who can access your notebook are the people who you want to be able to access those notebooks. Now, great, but it still doesn't tell me how do I actually work faster. So let's get into the details. Step 1, beefing up, scaling up. So if you use beefy hardware, Jupyter notebooks, you can create them to have extremely powerful configurations. You can have up to 160 virtual CPUs and up to almost 4 terabytes of RAM. That's a whole lot of processing power. And that's not it. You can include up to 8 of Tesla's V100 GPUs. These are extremely powerful beasts right here. Each one of these has over 5,000 CUDA cores and over 600 tensor cores at your disposal. And you can stick up to 8 of them on a single machine for massive levels of processing. Now, let's take a look at how this actually will work. So this is the Google Cloud interface for the Notebooks interface. And if you click on New Instance, you can see all the different flavors of notebooks that we offer. The TensorFlow Enterprise support, which we just released last week. TensorFlow 2.0, PyTorch, Rapids, CUDA, just plain CUDA without other stuff installed. And each of these come with GPU and non-GPU variants. And then you can also have just plain vanilla R and Python installed if that's what you prefer. But we want to look at just how beefy we can make these machines. So let's click on Customize Notebook and see just what we can do. So let's give this notebook a name. You can specify a region and a zone. The environment are the same flavors of notebooks that I showed you earlier. And here's where you can customize the notebook if you want with your own custom containers. And now you can choose just how powerful of a machine you want. You've got up to 160 CPUs and up to 4 terabytes of RAM. And you can choose different mix and match, different configurations, whatever floats your boat. And then for GPUs, you've got a bunch of different options, all the way from the simple K80s to V100s. You can pick whatever you want and choose up to 8 of those GPUs. And then to install the drivers, it's just a single checkbox, and you'll get those drivers installed for free. Now let's create that notebook. It'll take a couple minutes for this thing to create, and once it's done, you'll have a nice Open Jupyter Lab link over here, and you open that up, and you'll see your notebook on the spot. Now if you look at this, it shows you how you can create Python notebooks, but there is no R section over here. And you guys are all here looking for R. So most of our notebooks, other than this one right here, don't come with R pre-installed, but it's really, really easy to do so. So all you do is you just click on the notebook over here. That takes you into the VM that's backing the notebook. And over there, you can SSH into the notebook instance itself. And once you SSH into it, we'll just install a simple script over here. Just a single line. It'll download a script from GitHub. Trust me, it's safe. And it'll run it on your machine. And what this script does is it's just taking a few pip packages, a few apt-get dependencies that you have for R. It installs the R kernel, installs a couple of popular R packages in there. And then we also install XGBoost. Though the plain XGBoost that you get from CUDA or from CRAN does not come with GPU support enabled, so we have to compile our own version of XGBoost. But you guys don't have to worry about that complexity. The script takes care of all of that for you. So let's take the script. We'll go to our SSH terminal and run it, and there it goes. Now the script will take some time to run, so we won't wait for that to finish, but you guys can really easily use the custom container features I was showing you earlier to create your own custom containers of any of these flavors that have R pre-installed. We offer all these instances in a container form, so you just take that container, add a Docker file which runs that script at the end, and you'll have your own custom container ready built with very little work needed on your part. And then you can easily create those notebooks in just a couple minutes, just like you create the normal notebooks. So let's continue with the slides. Yeah, this is just the instructions on how to get the R installed. And now, using multiple machines, the next step, scaling out. So when you're using multiple machines, when you're creating a cluster of machines like this, you have huge levels of CPU and RAM at your disposal. Way more what you can get on a single machine, but it does come with a few challenges. First of all, you have to manage all these machines. You have to figure out, how do I get my data to those machines? How do I process the data on those machines? How do I aggregate back the results? That's a huge challenge right there. Fortunately, there have been a lot of patterns that have been established that help with this, specifically things like MapReduce and whatnot. So if you can make your code fit into one of those patterns, then you can use these machines without that much difficulty. You still have to do a lot of the management of the system itself, but that's where Google steps in and helps make things easier. We've got services like Cloud Dataproc, which is a managed Spark instance, and it takes care of a lot of the managed effort that you have to do to take care of those machines, so you can just focus on writing your code. There's also AI Platform's ML engine, which with ML engine, you write your code, write your model on your sample data sets. Then when you're ready to do your big training, with the full data, you just send the job off to ML engine, and ML engine will do all the heavy lifting, manage the heavy machinery for you. You don't have to worry about it at all. It's practically serverless. And then finally, we've got Google BigQuery, which is not your typical machine learning application, but it can be really useful for data analysis, and you can even use it for some of the pre-processing of your data. So let's take a quick look into BigQuery. With BigQuery, all you have to do is know how to write a SQL statement. And if you can write your query in a form of a SQL statement, then you can analyze your data in just 6 lines. And let's take a quick look at what BigQuery looks like. It's got a demo right here. Oh, by the way, once your R script finished installing, you'll see this little R show up in the launcher. And now, here's our BigQuery. So we're going to be querying Wikipedia sample data, and this table will contain the number of views to various Wikipedia pages between January to September 2010. So its data is about a decade old, but still good enough for our purposes. It's about 7 terabytes of data, so this is a massive amount of data to process. And what we're going to do, we just want to see, hey, what languages were most popular, and how much were they used? And we're going to split this up into showing us the top 10 most popular languages for every month. in our time period. So let's just run this query, and we're analyzing 7 terabytes of data, and we get back our results really, really fast. And you can just see it all charted over here. Most of the languages are kind of aggregated in this lower part right here, but one language had a whole lot of usage. I'll give you one guess as to what that language was. So, and that's how you can use BigQuery really easily. Now, GPUs, the moment you've all been waiting for. GPUs are highly, highly parallelizable. They have thousands of cores at your disposal, and it's all going to be on a single machine. So that takes care of a lot of the complexity of managing different machines. All that goes away. The time it took to pass data and algorithms back and forth, you don't have to worry about that. And it's also much cheaper than an equivalently large cluster. A cluster with 5,000 cores on it is going to be pretty expensive. And it's much faster than a cluster, assuming you're doing the right kinds of computations, which leads us to the challenges. First, GPUs are really optimal for linear algebra problems, but that's kind of the extent of it. So if you're going to use GPUs, you need to figure out, how can I change my problem? How can I remap it into something that's a linear algebra problem that uses matrices, that uses vectors? And that can take a little thinking to figure out, how do I adapt my problem into something of that nature? And you also had to use lower level APIs traditionally. So either you're writing CUDA drivers or you're doing matrix math directly. These are all different things that are a bit on the challenging side. And so those are things that are not insurmountable difficulties, but it does increase the bar to entry when you're trying to program on GPUs. And finally, setup can be a little bit challenging. First time I tried to install an Nvidia driver on my desktop, I spent the good part of an afternoon figuring out how to get that done. With notebooks, you saw we just needed one checkbox, and that was it. The drivers were installed automatically. And even the other challenges are starting to go away, and it's becoming easier. Just like how I mentioned earlier that there are packages which have been making it easier to write code that runs on multiple cores of your computer, there's packages now with higher level libraries that make GPUs easier to use as well. And this is true for both R and Python. And you can use these for various cases. So things like data processing and statistics, there's libraries called GPU tools and GPU R. Even for ML modeling and deep learning, there's TensorFlow, Keras, H2O.ai, XGBoost, MXNet, and Rapids. And there's much, much more than that. This is definitely not the entire list. And these are all different things that make it much, much easier for you to write code that will run on both CPUs and GPUs with the minimal changes necessary, if any. So how does code of that nature tend to look? Let's take a peek over here. So over here, I've got 2 notebooks set up. The one on the right is set up to use CPUs. The one on the left is using GPUs, and they're both using XGBoost. So over here, I'm creating some sample data, creating a matrix with 2 million rows and 50 columns. And this is the exact same code on the left and the right. And I'm going to create a boosted tree over here, a boosted decision tree. And the method that I'm using for this is the histogram method. And over here on the right is the exact same code. The only difference is that this is a GPU optimized histogram algorithm. Other than that, there is zero difference between the code on the left and the right. And you saw that the GPU version ran 5 times faster. It took just 2 seconds versus about 10 seconds for the CPU optimized one. And I'm expecting Nvidia will soon get rid of these 4 characters that you have to add and figure out if you have GPUs installed or not, so you don't even have to make that little change on your library. And that's it. That's all you have to do to switch between CPUs and GPUs and port your code to take advantage of the GPUs at your disposal. Let's look at a different example now. Let's go to TensorFlow with Keras. Installing Keras is really simple. You do need Keras pre-installed on the machine, which means that if you go back to the notebook's cloud console I showed you, you want to start off with a build that has TensorFlow installed on it. And then just one time only, you need to run this install Keras command. If you're using GPUs, say, add this extra parameter in there to say, hey, use a GPU optimized version of the binaries. And then you're off to the races. And so here, with Keras, let's get our data set. We're just downloading some data from MNIST. And we're going to just create our training and test data sets on there. And what we're going to do is we'll just run a neural network using Keras. And you see our network has about 3 layers. It has 1 unit. The first layer has 256 units. Second layer has half of that. And the last layer has 10 units. And the code in this case is exactly the same for both the CPUs and the GPUs. There's not a single byte that's changed between the left and the right. You see that the GPU version took about 18 seconds to run, and the CPU version took about 26 seconds to run. So that's still a significant speed up, but in the previous example with XGBoost, we saw a 5x speed up. This is nowhere near 5x. What's going on over here? Seems like we're not really using the GPUs to their fullest potential over here. So why is that? What's going on with this? Now, Scott Hanselman had said something once. He said, with every layer of abstraction, you became much more powerful if you understand the layer below it. And that's absolutely true when you're dealing with GPUs and matrix over here. So let's go. We've got these libraries that are hiding the complexity for us, but let's go one level deeper and see just what's going on underneath the hood. So do a little bit of introduction to basic matrix math. When you're solving a neural networks are represented as matrices under the hood. Each layer of the neural network becomes a matrix. And when you're passing data from one layer to the next layer, what's really going on in these algorithms is that they're multiplying the 2 matrices by each other. And when you're multiplying matrices, you take one row from the matrix on the left, one column from the matrix on the right. You rotate that column to match the row. You take each pair of numbers that are together, multiply those numbers, add up the results, and you put that final result in the output spot, which represents the intersection of that row and the column. And you repeat this process for all combinations of rows with all combinations of columns until you fill up the output matrix. Now, you'll notice from this is that each of these row and column multiplications is completely independent from each other. The output of one does not depend on the output of the other, which means there's a massive potential for parallelization over here. And that's kind of the thing that you want to keep in mind. And so now let's go into details over here using wider layers. If you add more and more rows to your matrices, which is what happens when you have wider layers, you're going to be taking advantage of much more parallelization potential over here. Because as we're adding more cores, simply having more cores doesn't just magically give you speed boosts. You need to have a data structure or an infrastructure that is actually capable of being parallelized to take advantage of all those extra cores. And nodes which have wider layers or wider nodes are prime candidates for taking advantage of those wider layers and using the parallelization options that are available. Note, this does not mean that wider layers will give you more accurate results when you're training, but if you need to use wider layers, that's when GPUs can really help you out. So let's go back to our code here on our notebooks and see what happens when we use wider layers. So let's kick this off. And now this code over here is the exact same code as we ran previously, exact same neural network. The only difference is that the first layer now has 4,000 units instead of the 256 units it had before. So it's a whole lot wider. But everything else is exactly the same. And as we will see just that the GPU version took about 20 seconds to run. And the accuracy is about the same, around 97%, which was the same as over here. But we didn't really get a speed up, which makes sense, because we're only telling this to do more work. We're not telling it to do less work. We're giving it a whole lot more work to do. But now, compared to the CPU version was already near its max capacity, so it's going to take a whole lot longer for the CPUs to run. And so to a caveat over here, you wouldn't want to increase the number of layers in your neural network just to make it look fast compared to a CPU. That's something you'd only do if you're doing a demo, like, I don't know, who does that? So this is still running. We'll come back to that once it's in a little bit. Oh, hey, there it's done. So it took 72 seconds for the CPU to finish executing. So went from 26 to 72, almost a 3x speed up, versus the GPU barely increased at all. So you can see just the potential. That's where we start using the potential of the GPUs over here. Now, let's go back over here. And another optimization, batching. So in the traditional way that you're taught in school, when you're running neural networks, when you're doing the training, you pass it one bit of data, you pass it down, you propagate it forward in your neural network, get to the end, calculate error, do the back propagation back up to the top, and you update your weights. When you're doing batching, you're doing the same process, but with multiple inputs being passed forward in parallel. So you heard the word, parallel. This is all happening in parallel, so you can take much better advantage of the extra cores because you're back propagating multiple units at once. And then you do some like averaging or some other algorithm you'll use to kind of figure out what the aggregated weight update should be. So this is another opportunity for you to just parallelize your work much better and take advantage of what the GPU cores are available to you. And what's better than batching? Larger batching. So you can do even more batches. If your GPU has more cores available, you can run your batches in even larger batches and get much, much larger workloads being done in parallel, take much better advantage of the GPUs. Of course, there's a point which batching will reach diminishing returns, so you have to play around to figure out what is the optimal batching level for you to get the right balance between speed of execution and accuracy of results. But that's something you can play around with and figure out what's going on. And this is just something to keep in mind when you're thinking of what are the different dimensions that I can have at my disposal to really maximize the uses of my GPUs while simultaneously getting as accurate of a result as you can. So let's take a look at that. So over here, let's go down to one more block, the bigger batches. We'll kick off these code blocks. And this is exactly the same as the previous version, except now we've increased our batch size 4x. Before it was 128 seconds, now it's 512. And now you're really seeing that speed boost for the GPUs. Instead of 20 seconds, we just took about 8 seconds to run the computations. CPUs are still chugging along. They will benefit from the bigger batches because we weren't fully maximizing the potential of the CPUs either. But you're really seeing what GPUs can do when you've got this batching built in. And, well, I guess let's not wait for that to run, but it takes about 40 seconds. Oh, there it goes, 40 seconds. So, and the accuracy is the same as it was before. So we can just quickly, yeah. So the accuracy wasn't affected at all. They're all about 70% or 97% accuracy, with all these different variations. Now, you want to make sure you're using the right tool for the job. I've given you many different tools. Each tool comes with its own pros and its own cons. Not every tool is going to be the right tool in every situation. Got to figure out what's the right tool for the job. Speaking of which, Rapids is a really impressive platform that Nvidia has created. It lets you execute entire data science workloads on your GPUs. Not just that, you can scale out to multi-node clusters where each cluster has multiple GPUs on it. So you're combining those different techniques that we talked about in the beginning to get absolutely unprecedented levels of computational power at your disposal. Now, the only downside is a lot of Rapids only works in Python, and I know you guys came here for R. But there's a way. You can execute you can execute both Python and R from the same notebook. You saw those Python packages that I was installing in the beginning of that script? This is what those things enable. You can write code in your Python notebook. You load this one extension. That gives you an R magic at your disposal, which lets you write R code in different cells. And you can even pass variables from Python to R and vice versa. So you can use Python for what Python is best at and R for what R is best at, getting the best of both worlds. So, in summary, there are 3 tactics that you can use to really increase your productivity. First off, scale up. Go to a much more powerful machine, the oldest, most classical answer, and you can compute much faster that way. Then if that doesn't meet your needs, then scale out. Go to multiple clusters, get much more CPU and RAM at your disposal, and finally, you can use GPUs for your workflows. And actually, really, the last bit is you can combine any of these options to get even more powerful configuration set up. Google Cloud Platform gives you the GPUs you need and the hardware you want on demand. You don't have to worry about provisioning and processing and purchasing. It gives it to you when you want it, and once you're done, you can turn it all off and you don't have to pay for it at all. And AI Platform Notebooks makes all of this really, really easy. And now what next? You can try it out. You can go to cloud.google.com, check out AI Platform Notebooks over there. All the code I showed you, it's available at GitHub at that above URL. And if you'd like to learn more about deep learning with R, there's a book called Deep Learning with R.